Somewhere beyond the limits of our perception, beyond the observable universe and the frontiers of modern physics, there may exist a dimension so fundamentally different from our own that it could be orchestrating every aspect of our reality without us even realizing it. What if the laws of physics, as we know them, gravity, time, space, even causality err, not universal constants, but rather the projected consequences of deeper, higher dimensional structures? For decades, physicists have explored the mathematical frameworks of string theory and M theory, proposing that our universe might be a three-dimensional membrane, or brain, floating in a vast, higher dimensional space called the bulk. According to these models, what we perceive as the universe is merely a slice, a lower dimensional shadow cast by something far more complex and possibly intelligent. And if such a higher dimensional structure exists, then could it be influencing not only the birth of galaxies or the motion of planets, but even the very nature of consciousness, time, and reality itself? Some of the latest theoretical work suggests that gravitational forces might leak into our universe from higher dimensions, subtly nudging the evolution of cosmic structures, warping space-time in ways we cannot yet measure, and possibly even seeding the Big Bang itself. This leads us to a disturbing but exhilarating implication. Our universe may not be self-contained. We may be embedded in a vast multiversal architecture, one where higher dimensional entities or systems act as cosmic programmers, setting initial conditions, manipulating fundamental constants, or even watching us unfold like a narrative written in the language of quantum fields. Think about quantum entanglement, a phenomenon Einstein famously called spooky action at a distance, where two particles separated by vast distances behave as if connected instantaneously. If we accept the possibility of higher dimensions, then this isn't spooky, it's geometry. What appears to us as instant connection across light years could be, from a higher dimensional vantage point, two particles touching in a realm where distance as we know it is irrelevant. And then there's the simulation hypothesis, which has gained traction among philosophers and scientists alike, from Nick Bostrom to Elon Musk, suggesting that what we experience as reality might be a computed projection generated by a vastly more advanced intelligence operating from a higher reality. But where would such an intelligence reside? Not in the clouds or cyberspace, but perhaps in a higher dimensional substrate that underlies and constructs our own. The fine-tuning of the universe, the delicate balance of constants like the gravitational constant or the cosmological constant, makes even the slightest deviation incompatible with life. Is this improbable harmony a coincidence, or is it the signature of deliberate calibration from a level of existence we cannot probe? Recent developments in quantum gravity and the holographic principle propose that everything we perceive as real could be a projection of information encoded on a distant boundary, much like a 3D image cast from a 2D surface. If that's the case, who or what wrote the code? Could this boundary be the interface between our brain and another? A canvas where higher dimensional dynamics paint the illusion of matter, space, and time. In this picture, we are not the main act, but the consequence of something much vaster, maybe even conscious. Imagine our cosmos not as the central stage of reality, but as a single ripple in a sea of multidimensional phenomena, each ripple potentially birthing its own laws, particles, and narratives. The idea of a controlling dimension isn't just speculative fantasy, it's becoming a mathematically consistent, testable extension of modern theoretical physics. Experiments with particle accelerators like the Large Hadron Collider are already searching for signs of extra dimensions, looking for tiny deviations in gravitational behavior or particle collisions that don't add up, like missing energy escaping into dimensions we cannot see. Gravitational waves, too, might one day reveal echoes of higher dimensional tremors that ripple through our spacetime like footsteps in the next room. Yet the true frontier may not lie in instruments, but in the architecture of thought itself, in reimagining the universe as not merely a place of matter and energy, but a construct emerging from information, logic, and unseen frameworks. Could consciousness itself be an emergent property of higher dimensional computation? Some scientists argue that the mind may not be entirely confined to the brain, but could be interfacing with other layers of reality, explaining phenomena like near-death experiences or quantum cognition. If true, our identities might not end at the borders of biology, but extend into domains we cannot yet access, dimensions that don't just influence matter, but thought, emotion, and will. The more we study the universe, the more it looks like a code governed by mathematical precision, elegant symmetries, and recursive patterns. But code implies a coder, structure implies an architect, and order implies a deeper intention. Could we be living in a reality guided not by randomness, but by purpose engineered from a realm beyond time itself? The question isn't merely whether another dimension is controlling our universe, but what control even means in a cosmos where the very fabric of reality might be emergent, conditional, or even illusory. Perhaps we are avatars in a cosmic interface, dreamers embedded in a hyperreal substrate, experiencing a story written in quantum ink on the skin of something infinite. And maybe, just maybe, the veil between us and this deeper truth is starting to thin, not through mysticism or fiction, but through equations, measurements, and the rising awareness that the universe is not the endpoint of understanding, but the beginning of something far greater. From the earliest days of human curiosity, our ancestors have looked up at the stars and wondered about their place in the vast tapestry of the cosmos. Long before the advent of telescopes or scientific theory, ancient civilizations such as the Babylonians, Egyptians, and Greeks began charting the heavens, noticing patterns in the motion of celestial bodies that hinted at an order beyond the chaos of daily life. These early skywatchers constructed elaborate cosmology's mythic stories and symbolic interpretations to make sense of the night sky. In ancient Greece, philosophers like Pythagoras and Plato proposed that the universe was governed by hidden mathematical harmony, a notion that would echo across millennia. Aristotle envisioned a geocentric cosmos, with Earth fixed at the center, surrounded by concentric celestial spheres. This model, later codified by Claudius Ptolemy in the 12th century AD, dominated Western thinking for over 1,000 years. It wasn't until the Renaissance that this anthropocentric view was challenged by a revolution in scientific thought. In the 16th century, Nicolaus Copernicus proposed a heliocentric model, placing the sun, not Earth, at the center of the known universe. His ideas, although controversial, set the stage for one of history's most dramatic shifts in perspective. The 17th century ushered in the age of telescopic astronomy with Galileo Galilei, who used his newly crafted telescope to observe the moons of Jupiter, the phases of Venus, and the rugged surface of the moon, observations that shattered the illusion of celestial perfection and lent powerful support to the Copernican model. Johannes Kepler refined this model further, showing that planets moved in elliptical orbits, not perfect circles, while Isaac Newton's laws of motion and universal gravitation provided a framework for understanding the dynamics of these orbits and, eventually, the motion of galaxies themselves. As the Enlightenment unfolded, a rational, mathematical understanding of the universe took hold. The universe was no longer seen as a divine enigma, but a mechanistic system governed by discoverable laws. By the 19th century, astronomers like William Herschel began mapping the Milky Way, speculating on the shape and structure of our galaxy. Spectroscopy revealed that stars were composed of the same elements found on Earth, bridging the gap between the heavens and our world. Yet, even with these revelations, the universe was still thought to be static, eternal, and relatively small. That changed in the early 20th century with a flurry of groundbreaking discoveries. Albert Einstein's general theory of relativity, published in 1915, redefined gravity not as a force, but as a curvature of space-time caused by mass and energy. This elegant theory allowed for dynamic models of the universe, models that could expand or contract over time. Around the same period, Vesto Melvin Slipher observed the redshift of distant galaxies, a subtle stretching of light that hinted they were moving away from us. But it was Edwin Hubble, in 1929, who confirmed that the universe was expanding, providing observational proof for a concept that would become the foundation of modern cosmology. The expanding universe implied a beginning, a moment when all matter, energy, space, and time burst forth from a singularity. This was the birth of the Big Bang theory, initially resisted by many but later confirmed by compelling evidence, including the discovery of cosmic microwave background radiation by Arno Penzias and Robert Wilson in 1965. This faint afterglow of the Big Bang, permeating the cosmos, was predicted by theorists as the leftover heat from the universe's earliest moments. It cemented the Big Bang as the dominant model, reshaping humanity's understanding of origin and scale. As technology improved, so did our reach into the cosmos. The mid-20th century saw the dawn of space exploration, with the Soviet Union launching Sputnik in 1957 and the United States landing Apollo 11 on the Moon in 1969. These events mark not just geopolitical milestones, but deep symbolic moments in our quest to transcend our planetary cradle. Robotic probes soon followed, exploring the outer planets and sending back data that expanded our understanding of the solar system's diversity and formation. The launch of the Hubble Space Telescope in 1990 transformed our view once again. With its unprecedented clarity, Hubble captured images of galaxies billions of light-years away, essentially allowing us to look back in time. It revealed the structure of the universe on a grand scale, showing us galactic clusters, nebulae, and gravitational lensing where light from distant objects is bent around massive bodies, confirming Einstein's predictions. During the same period, cosmologists began to refine measurements of the universe's expansion rate and discovered that not only was the universe expanding, it was accelerating. This shocking revelation, made in the late 1990s by two independent teams studying distant supernovae, led to the hypothesis of dark energy, a mysterious force pushing galaxies apart at ever-increasing speeds. Today, dark energy is thought to make up nearly 70% of the universe, while dark matter, an invisible form of mass that doesn't interact with light but exerts gravitational influence, comprises about 25%. That leaves only around 5% for all known matter, from stars and planets to people and particles. Alongside this cosmological progress, the concept of the observable universe became a central frame for understanding our limits. The observable universe is not the entire universe, but rather the region of space from which light has had time to reach us since the beginning of the cosmic expansion about 13.8 billion years ago. Due to the stretching of space itself, the observable universe has a radius of roughly 46.5 billion light-years in all directions, forming a sphere with Earth at its center. Not because we are the center of the universe, but because observation is always relative to the observer. This concept forces a humbling recognition. What we can see may be only a minuscule fragment of a much larger, possibly infinite cosmos. It also invites speculation about what lies beyond, from other regions with different physical laws to entire multiverses, each bubbling into existence like quantum foam in a higher dimensional space. The journey from mythological cosmologies to satellite-based measurements of cosmic background radiation reflects a profound shift not only in how we understand the universe, but in how we understand ourselves within it. We have moved from being passive observers of the stars to active explorers of the cosmos, sending machines to Mars, telescopes to orbit, and signals to the edge of the solar system. Each discovery builds upon the last, connecting ancient questions with cutting-edge theories in physics, mathematics, and astronomy. We now explore concepts like inflation, which suggests that the universe underwent exponential expansion in the first fraction of a second after the Big Bang, smoothing out irregularities and setting the stage for galaxy formation. We theorize about cosmic strings, higher dimensions, and holographic principles that suggest reality itself might be encoded on a boundary beyond our grasp. Through missions like the James Webb Space Telescope, we peered deeper into the early universe, detecting the light from the first stars and galaxies. Through experiments like those at CERN's Large Hadron Collider, we search for clues about the fundamental particles and forces that shape the universe in its infancy. And through gravitational wave observatories, we listen to the ripples of colliding black holes and neutron stars, cosmic events so violent they shake the very fabric of space-time. In this vast, expanding narrative, humanity's understanding of the universe continues to evolve. Each discovery acts like a new frame in an unfolding film, revealing more of the story while hinting at deeper layers still hidden from view. From ancient myths to mathematical models, from Earth-centered heavens to cosmic inflation, the journey reflects not just scientific progress, but a profound, ongoing quest to understand who we are, where we come from, and what lies beyond the visible edge of everything we know. We stand on a small blue marble, suspended in a cosmic ocean so vast it defies comprehension. And yet, despite its immensity, the universe has always called out to us in a voice that speaks not just to our intellect, but to something much deeper: emotions, our fears, our sense of wonder, and our longing for meaning. In the face of this grand scale, we are reminded of how tiny and fragile we truly are, but also how uniquely conscious we are of that fact. This awareness alone makes our existence extraordinary. The stars have always stirred something in you's an ancient echo, a pulse that beats in harmony with the rhythm of the cosmos. Looking up at the night sky isn't just an act of observation, it's an emotional confrontation with the infinite. It's in those moments of silence, under a sky ablaze with stars, that the big questions bubble to the surface. Why are we here? Are we alone? What happens after we die? And does any of this, our hopes, our struggles, our entire civilization, actually matter in the grand scheme of things? The universe doesn't just dwarf us. It magnifies our curiosity, challenging us to rise above our biological limits and seek truth not only through science, but through introspection, imagination, and shared wonder. People should care about the universe not just because it's beautiful or intellectually interesting, but because it touches the deepest parts of what it means to be human. The story of the cosmos is our story. We are made of stardust, forged in the hearts of ancient stars that lived and died billions of years ago. Every atom in your body, every carbon molecule in your DNA, every calcium crystal in your bones was born in a supernova. That isn't poetry, it's science. And yet it feels like poetry because it evokes awe and a connection that transcends logic. We are not separate from the universe, observing it from a distance. We are the universe, conscious of itself, asking questions no star or galaxy could ever formulate. And in that realization lies something sacred. To care about the cosmos is to care about our origins, our destiny, and our responsibility to preserve the only home we've ever known. When we send rovers to Mars, when we peer into the abyss of a black hole, when we detect gravitational waves from the collision of neutron stars, we're not just doing science, we're reaching across space and time to touch something timeless, something eternal. The emotional weight of the unknown is real. It's not just curiosity, it's also fear. The fear that we might never fully understand where we came from or where we're going. The fear that we are alone in this vast expanse. The fear that one day, everything we've built, everything we've dreamed, could vanish into entropy, swallowed by the cold darkness of a universe that doesn't care. But it's also that very fear that gives life urgency and beauty. The fleeting nature of our existence becomes precious. Like a candle flickering in the void, our short lives blaze with intensity because we know they won't last forever. The cosmic void is both terrifying and liberating. It strips us of illusions and leaves us naked before the truth. But in doing so, it also grants us the freedom to create our own meaning. When you realize that the universe doesn't owe you purpose, you also realize that you are free to forge one. You can love deeply, create passionately, seek knowledge relentlessly, not because the stars demand it, but because you do. The wonder of the universe is not in the answers it provides, but in the questions it ignites. Why is the speed of light constant? Why does gravity bend space-time? Why do quantum particles act differently when observed? These are not just technical puzzles, they are invitations to a greater conversation about the nature of reality and the role we play within it. Even the simplest stargazer, looking up in awe, participates in this conversation. That moment of childlike wonder, when you first learn that stars are suns and that some of the light hitting your eyes left its source before humans even existed, that feeling is the seed of every great scientific and philosophical breakthrough. It connects us across generations, across cultures, across lifetimes. Whether you are a scientist decoding the language of the cosmos or a dreamer simply staring into the night, you are part of something larger than yourself. There's also a profound emotional intimacy in the loneliness of space. The silence of the cosmos can feel like a mirror reflecting our deepest solitude, but it can also be a reminder of how rare and beautiful connection is. In the cold, indifferent universe, the fact that we can hold hands, share stories, create art, build civilizations that we can feel love, grief, hope, and despair is nothing short of miraculous. The cosmos doesn't have to care for us to care for each other. And perhaps, in that care, we express the universe's own potential for compassion through us. Maybe the consciousness that blooms on this planet is not a fluke, but a function away for the universe to feel, to ask, to long, and to grow. Every time we send a spacecraft into the unknown, every time we map a distant galaxy or model the shape of spacetime, we are extending the reach of human emotion, stitching threads of curiosity and courage into the cosmic fabric. Existentially, the study of the universe forces us to confront the ultimate questions. What is life? Is consciousness an accident? Or is it woven into the laws of reality? Are we a random outcome of cosmic probability? Or is there some underlying principle that favors life, thought, experience? And if we are alone, does that make our existence more or less significant? The emotional response to these questions is not trivial, it is essential. It determines how we live, how we treat others, and how we envision our future. If we are alone, then we are stewards of a rare gift. If we are not, then our place in the cosmic family becomes a mystery worth chasing for as long as we exist. Either way, the emotional drive to explore, to connect, to understand these are not distractions from science. They are the fuel. Even the idea of death takes on a new texture when viewed through the cosmic lens. In a universe governed by entropy, where stars are born and die, where galaxies collide and dissolve, our mortality is not a curse, it is part of the same process that makes the stars shine and the atoms dance. Just as a supernova must explode to seed the galaxy with the elements of life, we too must pass so others can rise. The emotional acceptance of this truth is not easy. It is tragic, but it is also profound. To live in full awareness of the universe's cold indifference and still choose to create beauty, to love deeply, to explore bravely, that is the essence of human resilience. It is an act of defiance, of hope, of courage, and it is deeply emotional. The cosmos also connects us culturally. Every civilization has looked to the stars and crafted stories, myths of gods and monsters, heroes and creation. These were not just entertainment. They were reflections of humanity's attempt to place itself in an incomprehensible world. Today, science carries that myth forward. The stories we tell about black holes, dark energy, and the multiverse are not void of emotion. They are charged with the same wonder that inspired ancient astronomers and dreamers. When we visualize the birth of a star or the collision of galaxies, we are participating in a cultural ritual as old as time, bearing witness to something larger than ourselves and feeling the shiver of the sublime. So why should people care about the universe? Because it is not just out there, it is in us, around us, and inseparable from us. Every breath you take is recycled stardust. Every thought you think is the result of particles interacting according to laws written in the early moments of time. To understand the universe is to understand the story of everything, of life, of death, of love, of loss, of beginnings and ends. And that story is not finished. We are writing it with every discovery, every question, every leap of imagination. It is not just a scientific pursuit, it is a human one, shaped as much by emotion as by evidence. In the end, caring about the cosmos is not just about exploring the unknown. It is about remembering who we are, where we come from, and what we might become. It is about finding meaning in the face of the infinite, wonder in the face of the void, and connection in the face of isolation. The universe may be vast and silent, but in our hearts, it speaks volumes. What if everything you've ever known, your thoughts, your senses, your understanding of time and spaces, just a fragment of something much larger, something you can't see, something we're only beginning to grasp? What if our universe is not the whole, but just a slicea ripple on a vast, multidimensional ocean whose currents flow beyond the reach of our perception? These aren't just the stuff of science fiction or late-night philosophy sessions. They are the real questions being asked by the most brilliant minds in physics, cosmology, and mathematics today. And they're not just questions for academics or researchers, they're questions for you, for everyone, because they challenge not only what we know about the universe, but what we believe about ourselves. So take a moment and ask yourself, if we were to discover that a hidden dimension is influencing or even controlling our universe, how would that change the way you see reality? Would it make you feel smaller? Would it make you feel like you're part of something greater, something more mysterious and beautiful than we ever imagined? This mystery, This possibility that we are embedded in a reality shaped by forces beyond space and time isn't just theoretical, it affects how we define existence itself. If higher dimensions exist, if the observable universe is merely a surface or projection of a deeper reality, then what we consider real might be no more than shadows on a cosmic wall. That realization would force us to question the fundamental nature of consciousness, free will, and even time. What does it mean to make a choice if that choice is already played out in a higher dimensional script? What is the soul, the mind, the I, if our thoughts are not self-contained, but resonating with vibrations from outside our dimension? These questions are not just abstract, they hit at the core of our identity, our beliefs, our philosophies, and our purpose. They call into question every assumption we've made about what it means to be alive, to be aware, to be human. So ask yourself this: if we are being influenced by a realm we cannot see, do we have the tools to detect it? Would we even recognize the signs? Could it be that certain anomalies in physics, the unexplainable behavior of particles, the fine-tuning of cosmic constants, the existence of dark matter and dark energy are not just unexplained errors, but deliberate signals, fingerprints of something intelligent, complex, and vastly more advanced than we can comprehend? Could déjà vu, intuition, or sudden creative insight be more than brain chemistry? Could they be echoes from another dimension? And if so, how do we even begin to build the language to describe such interactions? Think about the potential impact of such discoveries. If a new layer of reality were uncovered, it would ripple through every field: physics, biology, philosophy, art, even politics. The way we educate our children, the way we understand life and death, the way we treat each other could change dramatically. We would no longer be isolated in a cold, indifferent universe, but conscious actors in a layered, dynamic reality where thought and structure might intertwine in ways we cannot yet measure. We might learn that consciousness isn't a byproduct of neurons, but a universal field, that our minds tap into something that connects all living things, not just biologically, but energetically, dimensionally. What would it do to our religions, our spiritual beliefs, our sense of morality, if we found that intelligence exists beyond what we call life? And what if we found proof that we're not the only reality, that other universes exist, perhaps with entirely different physical laws, perhaps with other forms of life or other versions of ourselves? Would you want to know? Would you want to explore them? Or would it terrify you to learn that you are just one of countless iterations in an endless tapestry of realities? These aren't just sci-fi hypotheticals. They are becoming real possibilities as scientists build theories like brain cosmology, quantum loop gravity, and the multiverse interpretation of quantum mechanics. The more we discover, the more we realize how little we know. And that unknown, it's not a void, it's a frontier. A space for ideas, for dialogue, for imagination. So what do you think lies beyond the veil of the observable universe? Is there a boundary at all? Or are we simply too primitive to perceive what's already around us? Do you believe that time is a straight arrow? Or could it be folded, twisted, or even reversed in some higher dimensional framework? Is there a deeper logic to the universe we've only glimpsed through mathematics and symmetry? Or is it all chaos pretending to be order? Do you believe in fate, or do you believe in freedom? And if our universe is being influenced by a higher one, do we get to choose, or are we following a script written in dimensions beyond thought? These questions matter because they force us out of intellectual passivity and into a state of active engagement. They make us participants in the greatest mystery of our existence itself. They remind us that science is not just about equations or telescopes. It's about storytelling, about connecting dots, about daring to ask the questions no one else has asked yet. They bring science back to its roots, not just as a method, but as a philosophy of wonder. And it's not just about finding answers. Sometimes, the questions themselves are more important because they open our minds, challenge our assumptions, and spark conversations that transcend generations. We need more of these conversations. In classrooms, in living rooms, in art, in media. Because the more we talk about the unknown, the less it scares us. The more we engage with the mystery, the more we grow not just as individuals, but as a species. Imagine a world where children are taught not just to memorize facts, but to explore the edges of reality, to ask unanswerable questions, to feel the weight and wonder of the stars in their chest. Imagine a society that prizes not just intelligence, but curiosity, not just knowledge, but wisdom. This is what new discoveries can do. They can shift the entire human trajectory by giving us a bigger story to live in. So, don't just watch from the sidelines. Engage, debate, dream. What's your theory about the nature of the universe? Do you think consciousness is local or non-local? Do you believe reality is objective, or do you think we co-create it through observation and intention? Would you plug into a simulation if it offered answers, sir? Would you fight to break out of it and find what's real? The greatest adventure we've ever known isn't over, it's just beginning. And your voice, your perspective, your questions, they are part of this unfolding journey. Because in the end, we are all part of the same mystery. We are all reaching into the dark, hoping to find a signal, a pattern, a truth, and maybe, just maybe, the universe is reaching back. If you've ever stared into the night sky and felt something stir inside you, a question, a longing, a sense of home in the middle of nowhere, then you already know why this matters. It's not about finding final answers. It's about becoming the kind of beings who are brave enough to seek them. So let's explore the unknown, not with fear, but with fascination. Let's imagine new dimensions, not as escape, but as expansion. Let's keep asking impossible questions, because somewhere, out there, the answers might be waiting, and they might just change everything. Imagine the silence of space, not a quiet like anything we know on Earth, but an absolute, bone-deep silence that stretches across billions of light years. A silence so vast it wraps itself around galaxies, swallows stars whole, and expands endlessly with the accelerating breath of the cosmos. Out here, there are no up or down, no cardinal directions. Only the curvature of space-time itself, shaped by the massive structures that drift through the void like ancient gods asleep in a sea of ink. Picture yourself floating in the intergalactic abyss, far from the comforting light of our sun, surrounded by a panorama of cosmic majesty, spiral galaxies spinning with the grace of ballerinas, their arms swirling in golden tendrils of dust and stars, elliptical galaxies glowing like massive orbs of incandescent memory, irregular galaxies distorted by gravitational dances with others, caught in the tides of galactic evolution. Everywhere you look, light, some of it older than the Earth itself, is traveling, echoing through time, bearing witness to creation, collision, and collapse. Between these luminous islands lies something far more haunting: the void. Immense cavernous regions of near-perfect emptiness stretching for hundreds of millions of light years, where few galaxies exist and gravity holds its breath. These cosmic deserts aren't truly empty, but they are so lacking in structure that they feel like the universe's forgotten places, eerie reminders of scale and entropy. They punctuate the cosmos like negative space in a painting, emphasizing the immensity of all that surrounds them. And yet, even in these apparent abysses, dark matter remains a ghostly, invisible scaffolding upon which the universe is built. It does not emit or reflect light. We cannot see it, but we can feel it through the gravitational effects it has on everything else. Galaxies spin too fast to be held together by visible matter alone. Clusters of galaxies stay bound in ways that defy known physics unless dark matter is present. It is everywhere and nowhere, shaping the architecture of the universe without ever showing its face. Now consider the filaments of the cosmic web, immense structures made of dark matter and gas, stretching across the universe like veins in a living organism. At their intersections lie the richest clusters of galaxies, great nodal points where matter has gathered since the Big Bang. These structures reveal a universe that is not random but patterned, connected, alive in its own mathematical and physical harmony. Between the filaments and the voids, the universe breathes, evolves, and grows more complex with each cosmic second. Look deeper, and you'll see the remnants of cataclysm, the afterglow of the Big Bang itself, the cosmic microwave background, radiation faint but persistent, a snapshot of the universe when it was just 380 years old. It is everywhere, permeating space like a memory the universe cannot forget, cooling and stretching as time goes on, a whisper from the moment creation was born. Then there are the stars countless beyond counting, each one a nuclear furnace, some no bigger than a city, others 1,000 times the size of our sun. Some live fast and die young, exploding as supernovae, seeding the cosmos with the heavy elements needed for life. Others burn slowly, their fates sealed in quiet collapse, becoming white dwarfs or neutron stars, or black holes, those enigmatic objects from which not even light can escape. A black hole is more than a gravitational anomaly. It's a boundary in space and time, a one-way door to a region where the known laws of physics break down. And at the center of almost every galaxy, including our own, a supermassive black hole lurks, a dark heart of immense gravity, silently dictating the motion of millions of stars. Into this endless theater step the minds who dare to ask questions no other species has dared. Carl Sagan once said, "We are a way for the universe to know itself." And in that spirit, scientists like Stephen Hawking, Vera Rubin, Max Tegmark, and Kip Thorne have peeled back the veils of reality, revealing hidden dimensions, predicting the behavior of cosmic giants, and questioning whether time itself is fundamental or emergent. Rubin, for example, was instrumental in providing evidence for dark matter through her observations of galactic rotation curves work that shifted the course of astrophysics forever. Hawking gave us mathematical blueprints of black holes and boldly suggested they might not be eternal prisons, but objects that evaporate slowly over time. Thorne, a pioneer of gravitational wave science, helped bring Einstein's predictions to life a century after they were first imagined. And today, people like Brian Greene, Neil deGrasse Tyson, and Lisa Randall continue to inspire not only with their theories, but with their ability to translate the mystery into a language the rest of us can understand. The tone of the cosmos is one of contrast, violent, yet elegant, chaotic, yet ordered, incomprehensibly vast, yet governed by equations that fit on a chalkboard. Scientific curiosity in this realm is not dry or mechanical. It is a fire, fueled by awe, ignited by mystery, sustained by the relentless pursuit of truth. Imagine peering through the James Webb Space Telescope at the earliest galaxies ever, formed faint smudges of light, each one a thriving city of stars, more than 13 billion years old. Imagine detecting a gravitational wave from two black holes merging 1 billion light years away, feeling that ripple in the fabric of space-time pass through the Earth, whispering of an event so powerful it deformed the universe itself. These are not just discoveries. They are moments of communion with the cosmos. And it is this communion, this immersion, that defines the atmosphere of cosmology. You don't just study the universe. You live in it. You're made of it. You carry its story in your blood and bones. To dive into the cosmos is to stand at the threshold between the known and the unknown, to gaze across a sea of stars and feel both infinitesimal and essential. Because in a universe this vast, the fact that we can even comprehend a fraction of it is miraculous. The fact that we can wonder about it at all, that we can point to a patch of sky and say, that light left its source before the Earth had oceans, or that gravitational wave came from the death spiral of two objects we'll never see, is a testament to the singular power of human imagination and intellect. And so the atmosphere builds not as a static painting, but as a dynamic, living reality. It is punctuated by pulses of gamma rays, the steady blinking of pulsars, the spiraling arms of galaxies colliding, the undulating tension of quantum fields. The universe is alive with motion and rhythm, with mystery and clarity. It is a place where light is bent, where time is relative, where the very idea of nothing is pregnant with potential. Even vacuum is not empty, but teeming with virtual particles, popping in and out of existence. Even space is not flat, but curved by the presence of mass and energy. In this place of constant motion and unending possibility, we humans have begun to find our place not as the masters of the universe, but as its storytellers, its interpreters, its witnesses. And we do so with reverence, with humility, with joy, because the universe doesn't just exist to be studied, it exists to be felt, to be wondered at, to be dreamed through. And in every moment of curiosity, in every equation scribbled on a blackboard, in every late-night conversation under the stars, the atmosphere of cosmology deepens not just as a scientific endeavor, but as a human experience unlike any other. Somewhere, Buried in the equations and tangled in the photons arriving from the earliest galaxies lies a quiet, unsettling truth. We may never find the edge. Not because it doesn't exist, but because it may be beyond the grasp of any tool, any mind, or any method we possess. For centuries, science has promised that with better instruments, deeper insight, and more refined theories, the universe will slowly yield its secrets. But as we look deeper into the cosmic abyss, we are beginning to uncover not a well-lit corridor toward ultimate truth, but a hall of mirrors where each breakthrough reveals more uncertainty, each answer breeds new questions, and the notion of a final frontier begins to look more like a philosophical illusion than a scientific destination. The more we learn, the more reality resists simplification, folding back on itself in riddles that suggest our journey might not be about reaching an endpoint, but about learning to live in the tension of the unknown. The idea of an edge, whether spatial, temporal, or conceptual's, haunted cosmology since its inception. Is there a boundary beyond which the universe simply ends? Or are we inside an infinite structure, expanding forever, with no outer shell to cross? The concept of the observable universe already admits limitation. We are trapped inside a cosmic bubble, defined not by what exists, but by what we can see. Light takes time to travel, and because the universe is only 13.8 billion years old, we can only observe objects whose light has had time to reach us. Yet, due to cosmic expansion, that edge now lies 46.5 billion light-years away in every direction. Beyond that horizon, there may be more galaxies, more physics, even entirely different rules, but we will never know. That light is forever lost to us, stretched beyond detection, hidden behind a curtain of accelerating space. What lies beyond the observable may as well lie beyond time itself. And yet, even within the boundaries we can probe, signs of paradox abound, early warnings that our most cherished assumptions may be fundamentally flawed. Quantum mechanics, the framework governing the smallest scales, tells us that particles do not have definite positions or velocities until they are measured. They exist in a haze of probabilities, collapsing into form only under observation. Meanwhile, general relativity, Einstein's towering theory of gravity, treats the universe as a smooth, deterministic fabric shaped by mass and energy. But when these two theories meet in black holes, or the beginning of the universe, they explode into contradiction. Singularities form, places where density becomes infinite and our math falls apart. Space and time become meaningless. These breakdowns aren't minor, they are catastrophic warnings that our models, no matter how successful, are incomplete. Physicists have spent decades trying to reconcile this rift, searching for a theory of everything that would unite the quantum and the cosmic. String theory, with its extra dimensions and vibrating filaments of energy, seemed to promise just that. But its complexity and lack of empirical testability have left it stranded in a realm where mathematics outpaces measurement. Loop quantum gravity, another contender, tries to quantize space-time itself, treating space as a granular structure rather than a smooth continuum. Yet here too, progress has been slow and riddled with unresolved problems. Even our most ambitious theories may be glimpses through a fogged window, only partial views of a reality whose true nature is stranger than we dare imagine. Observational constraints deepen the crisis. Take dark energy, a force driving the accelerated expansion of the universe. We can measure its effects, but we don't know what it is. It isn't matter. It isn't energy in any traditional sense. It doesn't clump or flow, it just exists in the vacuum of space with a negative pressure that defies intuition. Our models include it, but our understanding doesn't. Or consider dark matter, which holds galaxies together yet refuses to interact with light. We can't see it, touch it, or isolate it. We infer its presence from its gravitational effects, but its true nature remains one of the greatest mysteries in physics. We may be surrounded by invisible scaffolding billions of solar masses in every direction, yet remain blind to its origin. The cosmos is full of shadows cast by things we cannot touch. And then there are the anomalies. The cold spot in the cosmic microwave background, an unusually large, unusually cold region in the afterglow of the Big Bang has puzzled cosmologists for years. Is it a statistical fluke? A window into another universe? A hint of exotic physics at work? No one knows. Or the Hubble tension, a disagreement between two methods of measuring the universe's expansion rate, one using distant supernovae, the other using the cosmic microwave background. Both methods are precise. Both are backed by independent evidence, but they don't agree. Not by a little, but by enough to suggest that something fundamental might be missing from our model of the universe. Perhaps our understanding of cosmic time is flawed. Perhaps gravity behaves differently over vast distances. Or perhaps we are staring at a crack in the foundation of modern cosmology. These cracks, these paradoxes, are not failures. They are invitation calls to question the axioms we take for granted. But they also whisper that the universe may not be built for our understanding. Our brains evolved to navigate savannas, not supernovae. Our senses evolved to detect predators and food, not gravitational waves or quantum fields. The fact that we can grasp even a sliver of the cosmos is astonishing, but there may be limits to what we can ever know. Gödel's incompleteness theorem showed that in any consistent mathematical system, there will be truths that cannot be proven. Might the same be true for physics? Might there be aspects of the universe that are true but forever inaccessible to experiment, unreachable by logic, unprovable by any method we can invent? Even time, the most basic of experiences, defies comprehension. In relativity, time is not absolute, but relative to the observer's motion and gravity. In quantum mechanics, time barely features at all, reduced to an external parameter. Some theories suggest time might be emergent, not fundamental, a side effect of deeper timeless laws. Others suggest time might loop, fragment, or even disappear entirely in extreme conditions. So how can we claim to understand the universe if we don't even understand the dimension through which we live our entire lives? These are not just technical puzzles. They are existential confrontations. They remind us that no matter how many satellites we launch, no matter how many particles we smash, the cosmos may always be one step ahead, laughing, elusive, unknowable. And still we search, still we dream, still we build machines to trap light from the dawn of time and write equations to bend space on a chalkboard. But deep down, we must wrestle with the truth. Our pursuit may not lead to a final answer. There may be no grand unifying revelation, no moment when the universe finally makes sense in a neat, complete way. Instead, we may find ourselves wandering forever at the edge of comprehension, building better maps of a terrain that never stops shifting. And maybe that's the point. Maybe the value lies not in what we find, but in the act of seeking itself in the endless dance between curiosity and mystery, between the questions we ask and the limits we crash into. For every satellite launched, for every theory proposed, there is a horizon we cannot cross. The speed of light imposes a hard barrier. The uncertainty principle forbids absolute precision. The horizon of a black hole hides all information. And beyond the observable universe, beyond the reach of any signal, lies a darkness so profound it may never be pierced. Perhaps the true conflict isn't between theory and data, or between competing models. Perhaps the conflict is between what we crave, a complete, unified understanding, and what reality offers: endless depth, infinite nuance, and the humility to accept that we are travelers in a mystery too vast to master. And yet, what a journey it is. The absence of certainty does not mean the absence of meaning. If anything, it deepens the meaning. The edge may forever recede, but the chase brings us together. It sharpens our minds, stirs our hearts, and reminds us that to be human is not to know everything, it is to be willing to ask, even in the face of silence. So when we speak of the edge of the universe, we are also speaking of the edge of ourselves, of what we can understand, what we can imagine, and what we dare to confront. And in that shadowy borderland where knowledge ends and wonder begins, the real story unfolds not of a universe waiting to be conquered, but of a species brave enough to keep asking why. In the grand theater of the cosmos, the deepest conflict is not between galaxies or dark forces, it is within us, between the stories we tell about the universe and the evidence that resists them. This is a conflict born not of ignorance, but of too much knowledge, of theories that stretch in opposite directions, of equations that refuse to settle into harmony. At the heart of modern cosmology lies a profound tension. How do we define the edge of something that may have no edge. Is the universe infinite or finite? Is it closed like a sphere, looping back on itself, or open like a plane that stretches forever? And more urgently, how do we reconcile what we observe with what our theories predict, when they no longer agree on the most basic principles? These questions are not just academic, they are the front lines of a war for truth, where physicists, cosmologists, and mathematicians battle not only the limits of the universe, but the limits of their own understanding. On one side of the battlefield stand the champions of general relativity, the theory that has explained the motion of planets, predicted black holes, and passed every experimental test thrown at it. Einstein's equations describe the curvature of space-time itself, and they offer models of the universe that are elegant, deterministic, and continuous. But general relativity is a classical theory, one that breaks down at quantum scales, particularly at singularities such as the heart of a black hole or the first instant of the Big Bang. In these regions, the fabric of space-time is torn, and relativity has no answers. On the other side stands quantum mechanics, a theory of probabilities, uncertainty, and discrete units of energy. It works flawlessly at the scale of atoms and particles, but struggles to describe gravity or the large-scale structure of the universe. Quantum field theory tells us how particles interact, how forces behave, and how the vacuum teems with virtual fluctuations. But it cannot, on its own, explain why space-time exists or how it behaves in extremes. The tension is clearest when we try to understand the origin and possible boundary of the universe. The standard model of cosmology describes a universe that began in a hot, dense state and has been expanding ever since. But what came before the Big Bang? Was there a before? Relativity implies that time itself began at that moment, making before meaningless. But quantum mechanics suggests that something must have existed, some field, some potential, some fluctuation that triggered the expansion. Attempts to unify these ideas have produced a zoo of theories: string theory, M theory, loop quantum gravity, causal dynamical triangulations. Each offers glimpses of a deeper reality, but none has achieved experimental verification, and each paints a very different picture of the cosmic edge. String theory proposes that the universe is composed of tiny vibrating strings existing in 10 or 11 dimensions. In some versions, our entire visible universe is a three-dimensional brain floating in a higher dimensional bulk. Collisions between brains could cause Big Bang-like events, suggesting a cyclical or infinite series of universes. But these extra dimensions are unobserved, folded up at scales far beyond current experiments. Critics argue that string theory is untestable, more mathematics than physics, a beautiful structure with no tether to reality. Meanwhile, loop quantum gravity attempts to quantize space-time itself, replacing the smooth continuum with discrete chunks or loops. This theory avoids singularities by proposing that space and time break down into fundamental units, no smaller, no smoother. In this view, the universe could bounce rather than bang, emerging from a previous contracting phase. But again, direct evidence remains elusive. And so the war continues not just between competing theories, but between theory and observation. Consider the flatness problem. Measurements of the cosmic microwave background suggest that the universe is geometrically flat, yet that flatness would require extremely precise initial conditions, a kind of cosmic fine-tuning that feels unnatural. Inflation theory was introduced to solve this, proposing a brief period of exponential expansion just after the Big Bang. This explains flatness, horizon uniformity, and the distribution of galaxies. But inflation itself is speculative, with many different versions and no direct confirmation. It also opens the door to eternal inflation, a process in which inflation never fully ends, creating an infinite multiverse of bubble universes. This offers an explanation for why our universe has its specific properties. We live in one of the bubbles where the conditions happen to support life, but it also makes predictions impossible to verify. How do you test for other universes when their light can never reach us? This leads to a deeper philosophical clash between those who believe that a theory must be empirically testable to be meaningful, and those who argue that mathematical consistency and explanatory power are sufficient, at least for now. The multiverse is a perfect storm for this conflict. It elegantly explains fine-tuning, cosmic coincidences, and the anthropic principle, the idea that we observe this universe because it's the one compatible with our existence. But it offers no falsifiable predictions. It is, in effect, a scientific narrative that explains everything and nothing. Critics claim this is not science, but metaphysics. Defenders argue that it is the inevitable conclusion of inflationary models and string theory's landscape of possible vacua. The debate grows fiercer when we examine the nature of the observable universe itself. Our instruments detect light from 13.8 billion years ago, but because space itself is expanding, the actual size of the observable universe is closer to 93 billion light-years across. This is not the size of the whole universe, only the part we can see. Beyond that lies unobservable territory, potentially infinite, potentially repeating, potentially unknowable. If the universe is infinite, then all possible configurations of matter may exist somewhere. There may be another Earth, another you, living a slightly different life. If it is finite, then what lies beyond? A boundary? A fold? A higher dimensional substrate? No evidence settles the question. The observable horizon traps us inside a bubble of uncertainty, and the laws of physics prevent any signal from escaping or arriving from beyond. Even the speed of light, once seen as a fundamental constant, becomes a barrier. It limits what we can observe, what we can affect, and what can affect us. As the universe expands faster and faster, more galaxies cross beyond our horizon every day, disappearing not because they cease to exist, but because their light will never reach us again. We are not just surrounded by darkness, we are sinking deeper into isolation, cosmically alone. If the expansion continues indefinitely, future civilizations may see only a black sky, with no evidence of other galaxies, no microwave background, no trace of the Big Bang. Our own cosmic context may become a lost memory, and the question of the edge may be not just unanswered, but unaskable. Amidst all of this, cosmologists struggle not just to define the edge, but to define the terms of the debate. What counts as evidence? What constitutes a meaningful question? Is what came before the Big Bang even a valid inquiry? Or is it like asking, what's north of the North Pole? Some theories suggest that time itself is emergent, that it comes into being only in certain conditions and ceases to exist in others. Others posit that time is an illusion altogether, a trick played by entropy and memory. If we don't understand time, how can we claim to understand beginnings or boundaries? The conflict reaches its most dramatic point in the realm of black holes, nature's own edge cases. When matter collapses beyond a certain density, it forms an event horizon, a boundary beyond which nothing can return. According to relativity, this is a one-way trip. According to quantum theory, information cannot be destroyed. The resulting contradiction, known as the black hole information paradoxus, haunted physicists for decades. Some propose that information is stored in the event horizon, encoded in subtle quantum fluctuations. Others suggest that black holes evaporate slowly, releasing the information through Hawking radiation. Still others believe that black holes are gateways to other regions of the universe or other universes entirely. But no one knows. The conflict is not just about black holes. It is about the fundamental consistency of our two greatest theories. If they cannot agree on what happens at the edge of a black hole, how can they agree on the edge of the universe? And so, in laboratories, observatories, and lecture halls, the debate rages on. Some seek a grand unification, others seek empirical anomalies that might point the way. Some are content with models that work, even if they conflict in principle. Others demand deeper coherence, but no consensus has emerged. The edge remains undefined, not just physically, but intellectually. It is not a line we can cross, but a question we cannot resolve. And yet, we keep asking. Because the conflict is not a flaw, it is the engine of progress. It is what drives us to invent, to imagine, to refine. The greatest discoveries are born not from certainty, but from the friction between opposing ideas. In the end, the tension between theories is not a sign of failure. It is a sign that we are approaching something fundamental, something the universe does not yield easily. Like tectonic plates grinding beneath the surface, the clash of ideas builds pressure that may one day erupt into revelation. Until then, we live in the fault lines, in the space between competing truths, in the beautiful, terrible gap between what we know and what we cannot yet imagine. That is the true edge-not of boundary in space, but the border between comprehension and mystery. And it is there, in that liminal space, that the future of cosmology will be forged. What if the universe has no edge? Not in the poetic sense of being boundless or mysterious, but in the most literal, defiant sense that there is no boundary to reach, no outermost layer to breach, no final truth to uncover? What if our cosmic quest is not a journey toward a definable horizon, but an endless immersion in depth, where every layer peeled back reveals not a core, but more layers? If the universe truly has no edge, if it is infinite in extent, eternal in some form, or cyclical in nature, then the consequences are more than conceptual. They redefine the purpose of science. They challenge the very architecture of knowledge. They force us to confront an uncomfortable possibility that ultimate understanding may remain forever out of reach, not due to our failure, but due to the nature of reality itself. In physics and cosmology, the absence of an edge shatters old assumptions. Traditional scientific models rely on boundaries, initial conditions, final states. The Big Bang is one such boundary, a temporal edge that frames the universe's beginning. Black holes represent spatial boundaries where our equations fail. The speed of light defines the causal boundary of what we can know. Even the observable universe is, by definition, a region with a perceptual limit. We are trained to search for edge cases, for exceptions, for frontiers. But what if nature doesn't offer us a final page? What if space goes on forever, time loops or dilates into meaninglessness, and the fundamental rules themselves are local, applying only within our bubble of cosmic experience? Then the quest to unify everything might not just be difficult, it might be impossible. In such a reality, our theories lose their foundation. An edgeless universe undermines the notion of a singular origin. It renders meaningless the idea of before and after, center and edge, here and elsewhere. It challenges the idea that we can contain the cosmos within equations, written on chalkboards or simulated on quantum processors. An infinite, edgeless cosmos means that every explanation we craft is inherently local, possibly provincial, a model that works in our patch of existence but may unravel in a different sector of the cosmic quilt. This devastates our deepest ambitions in physics to find universal laws that apply everywhere, everywhen. If those laws are emergent, relative to cosmic conditions, or shaped by some deeper logic we can't access, then our current models, no matter how beautiful, are approximate at best. Newtonian physics worked until it didn't. Relativity works until it meets the quantum. Quantum works until gravity enters the room. The pattern is clear. Every truth has its domain. But in an edgeless cosmos, there may be no final domain, no frame large enough to contain all others. This is not just a scientific frustration, it is a philosophical earthquake. For centuries, we have believed that with time, reason, and data, we could converge upon truth. That science would slowly sculpt away the illusions, revealing a naked, objective reality. But what if the truth is not singular, not fixed, not even fully knowable? What if the universe is not a puzzle with a solution, but a canvas without margins? The implications are staggering. Without an edge, meaning must be constructed, not discovered. Reality becomes participatory, interpretive. The act of observing shapes the observed not just in quantum mechanics, but in cosmological terms. We are not just deciphering a code. We may be part of its syntax, its grammar. The universe doesn't end, but neither do the questions. And that endlessness becomes both a curse and a gift. In this paradigm, new physics isn't just desirable, it's necessary. Our current frameworks are powerful, predictive, and mathematically rigorous, but they are incomplete. They cannot reconcile quantum uncertainty with relativistic curvature. They cannot explain what dark matter is, what dark energy does, or why the cosmological constant is so absurdly small yet non-zero. They cannot tell us why there is something rather than nothing. These gaps are not details, they are signals. Signals that we're using the wrong tools for the job, that our assumptions are too constrained, that our epistemology needs an upgrade. To move forward, we may need to abandon the comfort of determinism, the elegance of symmetry, even the primacy of time. We may need theories that incorporate information as a fundamental building block, not just energy and matter. We may need to redefine space not as a passive backdrop, but as an emergent property of relationships, entanglements, and causal networks. Consider the implications of a holographic universe theory gaining traction in string theory and quantum gravity. In this model, everything we perceive as three-dimensional could be a projection from a two-dimensional boundary, much like a hologram. If true, then edge becomes a misnomer. The edge may be an illusion, a construct of our dimensional perception. We are shadows on a higher dimensional wall, and our laws of physics are reflections of a deeper algorithm we cannot yet decode. Or consider the idea that space-time itself may be emergent, arising from quantum entanglement. This view flips everything on its head. Particles are not moving through space. Space exists because of how particles are entangled. Time flows not because clocks tick, but because information decoheres. In such models, the edge is not a place. It's a phase transition, a shift in the rules, a boundary of concepts rather than coordinates. The existential impact of these ideas cannot be overstated. If the universe has no edge, then there may be no outside to escape to, no higher vantage point from which to see the whole. That can be terrifying. It means we may never solve the universe. We may never reach a final theory. We may never know whether we are alone or one of many. But it also means that our journey is open-ended. That wonder never runs out. That discovery is infinite. In a finite universe with edges, meaning could be located at the boundaries, the beginning, the end, the ultimate cause. But in an infinite universe with no edges, meaning is found in motion, in process, in becoming. The universe is not a story with a final chapter. It is a song that never stops playing, a pattern that never fully repeats. This reorients human identity. We are no longer the center of the cosmos, but neither are we insignificant. We are rare concentrations of complexity, of self-awareness, of inquiry in a sea of silence. Our fragility becomes our strength. Our curiosity becomes our compass. In a boundless universe, the urge to understand, to explore, to feel awe, these are not luxuries. They are evolutionary imperatives. They are how we navigate a reality with no map. And maybe that's the truest meaning of science. Not the pursuit of closure, but the cultivation of eternal openness. A way of staying in conversation with a universe that will never stop whispering new questions. So we return to the edge, not to cross it, but to reconsider what it is. Maybe the edge is not where the universe ends, but where our comprehension falters. Maybe it's not a wall, but a mirror showing us our own limits, our own myths, our own hunger to know. And maybe, by staring into that edge, by leaning into the paradoxes, the anomalies, the contradictions, we begin to grow. Not by answering everything, but by living in a state of deeper, more resilient wonder. The universe without an edge is not less meaningful. It is more, because it means the horizon never closes. The questions never run dry, and the adventure of being alive, being aware, being part of this cosmic riddle never ends. There comes a moment in every journey when the narrative shifts, when the old questions give way to new ones, when a single discovery cracks open 1,000 possibilities, when the entire trajectory of exploration pivots toward uncharted territory. In the story of cosmology, that moment, the turning point, didn't come with a bang, but with a quiet, almost imperceptible observation. The universe isn't just expanding, it's accelerating. This revelation, made in the late 1990s by two independent teams of astronomers studying distant Type Ia supernovae, didn't just tweak our model set, shook the foundations of everything we thought we knew about the fate, the shape, and the nature of the universe. Until then, scientists believed that the expansion of the cosmos, triggered by the Big Bang, would eventually slow down, maybe even reverse under the pull of gravity. But the data said otherwise. The galaxies weren't just drifting apart, they were being pushed. And whatever was doing the pushing wasn't matter, wasn't light, wasn't anything we could see or measure. It was something else, something new, something that would come to be known as dark energy. The discovery of dark energy was more than a plot twist. It was the birth of an entirely new chapter in cosmology. Suddenly, the vast majority of the universe was invisible not only to our eyes, but to our theories. Around 5% of the cosmos is made of ordinary matter stars, planets, dust, us. About 27% is dark matter, which we infer through gravitational effects but have never directly detected. The remaining 68%? That's dark energy, a force with no known particles, no confirmed mechanism, no anchor in the standard model of particle physics. Yet it shapes the fate of the cosmos on the largest scales. It's the driver behind the accelerating expansion of space itself, and its discovery has forced cosmologists to abandon the comforting idea of a knowable universe governed entirely by the visible. Now, we live in a cosmos dominated by the unknown. This dark energy appears to behave like a property of space itself, a uniform, non-clumping pressure that increases as the universe expands. As more space is created, more dark energy appears, pushing even harder, leading to a feedback loop of acceleration. It's as if the fabric of reality is being inflated from within. This has profound implications, not just for the future of the universe, but for our ability to understand it. If acceleration continues indefinitely, the cosmos may end in a big freeze or heat death, where galaxies race beyond each other's horizons, stars burn out, and even black holes evaporate, leaving behind a cold, silent expanse of entropy. But if dark energy is not constantive, it changes with time. It could result in a big rip, where the very bonds of matter are torn apart as space accelerates faster and faster. These are not philosophical speculations. They are testable consequences of a universe driven by dark energy. And so, this revelation did more than expand our view. It redefined the stakes. The turning point is also technological. With every new tool we build, we peel back another layer of the cosmic veil. The Hubble Space Telescope, launched in 1990, marked the beginning of this modern era of deep space exploration. Floating above the blur of Earth's atmosphere, Hubble delivered unprecedented clarity, capturing galaxies as they were billions of years ago, revealing the large-scale structure of the universe, and measuring the expansion rate with astonishing precision. But Hubble was only the beginning. The Planck satellite, launched by the European Space Agency in 2009, mapped the cosmic microwave background, CMB, with exquisite detail, providing a baby picture of the universe just 380 years after the Big Bang. These maps confirmed the basic predictions of the Big Bang model, but also revealed subtle anomalies, strange asymmetries, cold spots, and fluctuations that didn't quite fit the expected pattern. These quirks remain unexplained and may point toward new physics lurking just beyond the horizon. Then came the James Webb Space Telescope, JWST, a technological marvel decades in the making. Launched in December 2021, it quickly began returning images and data that challenged long-held assumptions. JWST peered deeper into the early universe than any instrument before it, spotting galaxies forming earlier and more rapidly than models predicted. Some of these galaxies appear too massive, too structured, too bright for their age-raising questions about how quickly matter clumped together after the Big Bang, and whether the laws of galaxy formation might need revision. These aren't minor anomalies. They suggest that our understanding of the early universe, of star formation, and possibly even of the nature of dark matter may be incomplete. The revelations keep coming. JWST also spotted evidence of complex organic molecules in the atmospheres of exoplanets' carbon-bearing structures, like those that form the building blocks of life. These findings don't prove the existence of extraterrestrial life, but they hint that the conditions for life may be more common than we once believed. This forces us to widen our lens. Not only are we trying to understand the universe's origin and fate, but we're increasingly focused on its potential for life. What was once a fringe topic, astrobiology, is becoming central to our exploration, further complicating the cosmological story by adding a biological dimension to the physical one. Other technologies have deepened the turning point. The Laser Interferometer Gravitational Wave Observatory, LIGO, for instance, has opened a new window on the cosmos, listening to the universe rather than just looking at it. In 2015, LIGO detected gravitational waves from the merger of two black holes, confirming a century-old prediction of Einstein's general relativity. Since then, dozens of such events have been detected, including neutron star collisions that produce both gravitational and electromagnetic signals. These multi-messenger events offer a richer, more nuanced view of the universe, enabling us to study matter under conditions impossible to replicate on Earth. They also provide another method of measuring the expansion rate, potentially resolving or deepening the conflict between different measurements of the Hubble constant, known as the Hubble tension. The more we measure, the more we discover tensions. The universe is no longer a neat equation. It's a discordant symphony, beautiful, but out of tune. The Hubble tension, the discrepancy between local and early universe measurements of expansion, is one such discord. It's not a small disagreement. It's a growing chasm that suggests our standard cosmological model, the lambda cold dark matter (LLCDM) model, may be missing key components. Are there unknown particles? Is dark energy dynamic changing over time? Is our assumption of homogeneity treating the universe as the same everywhere at large scales breaking down? These questions are at the heart of a new scientific era, one defined by humility in the face of data that won't conform. Another unexpected finding is the uniformity of the CMB, despite the limited time light had to travel in the early universe. This horizon problem led to the theory of cosmic inflation, a brief burst of exponential expansion that smoothed out the wrinkles. But inflation remains a theoretical scaffolding. There are many versions of it, and no direct evidence for any. Some physicists now argue for alternative models, bouncing cosmologies, ekpyrotic universes, or holographic inflation, all radically different scenarios, each with its own set of implications for what the universe is and how it came to be. All of these developments, dark energy, JWST anomalies, gravitational waves, tensions, and data are not just steps forward. They represent a shift in the terrain itself. We are no longer filling in gaps of a nearly complete picture. We are uncovering cracks that suggest we may need a new frame altogether. This is the true turning point, not just in what we know, but in how we know. The cosmological narrative is shifting from one of confirmation to one of confrontation. We are not just testing old models. We are preparing to replace them. We are standing on the threshold of a new theoretical frontier that may require us to abandon cherished assumptions, to rethink time, space, matter, and even causality. And yet, there is something profoundly human in this moment. In the face of a universe that grows stranger the more we learn, our response is not to retreat, but to lean in. We build better telescopes. We design more sensitive detectors. We ask deeper questions. The turning point is not an end. It is an opening, a signal that we are entering a new phase in the cosmic journey, one where mystery is not a barrier, but a beacon. What comes next may redefine our species' place in the universe, not just as observers, but as meaning makers, as pattern seekers, as explorers in a story that has only just begun. What if everything we thought we knew about the universe, about matter, space, time, even reality itself, was based on a flawed assumption? What if our persistent confusion in cosmology stems not from a lack of data, but from the limits of our perspective? In science, as in life, progress often begins not with new answers, but with new questions, especially questions that challenge the foundation beneath all others. In the search for the edge of the universe, the nature of dark energy, or the true structure of space-time, we may not be facing a dead end at all. We might be facing a mirror that reflects not the failure of our tools, but the need for a deeper shift in how we interpret what we see. Sometimes, the most revolutionary discoveries don't come from more powerful telescopes or better measurements, but from a radical change in the questions we dare to ask. This shift is already underway. As physicists wrestle with conflicting measurements, strange anomalies, and incompatible theories, a growing number of them are beginning to suggest that we may be looking at the entire problem from the wrong angle. One of the most provocative and promising avenues for this shift is the holographic, principally bold idea that suggests everything we perceive as three-dimensional may actually be encoded on a two-dimensional boundary. Like a hologram, where a flat surface projects a 3D image, our entire universe may be a projection from a deeper, lower-dimensional reality. Originally proposed by Gerard Tooft and developed further by Leonard Susskind, the holographic principle was born from attempts to solve the black hole information paradox, the problem of how information is preserved in a system where classical physics says it should be lost forever. According to the holographic principle, the information inside a black hole is not destroyed, but somehow encoded on the surface of its event horizon. This principle was expanded to suggest that the same could be true for the entire universe. If so, the edge of the universe may not be a spatial frontier, but a metaphysical surface on which the information of our reality is stored, while everything we experience is a kind of emergent illusion. This idea gained traction with the advent of the ADS-CFT correspondence, a duality discovered in string theory by Juan Maldacena in 1997. In this framework, a gravitational system in a higher dimensional bulk space can be fully described by a quantum field theory on its lower dimensional boundary. Though our universe is not an anti-de Sitter space, ADS, the underlying logic may still apply, offering a new lens through which to view everything from gravity to the expansion of space. The implications are staggering. If reality is holographic, then space itself is not fundamentality, is derived from more basic principles, perhaps linked to information theory, entropy, or quantum entanglement. Time, too, might not be a fixed dimension, but a construct that emerges from correlations between quantum states. In this view, the cosmos is not a static container in which matter moves, but a dynamic, self-generating web of information that gives rise to the appearance of continuity, depth, and motion. If this sounds more like philosophy than physics, it's worth noting that these ideas are increasingly supported by serious mathematical models, and they may offer the only coherent path forward as we seek to reconcile general relativity with quantum mechanics. But how did we end up here, reimagining the universe as a quantum projection? The answer lies in the struggles of our current models. Quantum mechanics and general relativity, the twin pillars of modern physics, describe vastly different worlds. Quantum theory operates in the realm of the small particles, probabilities, uncertainty. Relativity describes the larger stars, planets, galaxies, space-time curvature. Each is fantastically successful within its own domain, but they break down when forced to coexist. In black holes, in the Big Bang, at the Planck scale, this conflict isn't just theoretical, it's epistemological. It forces us to consider that the problem may not be the theories themselves, but our attempt to shoehorn them into a framework that assumes space and time are fundamental. What if they're not? Quantum entanglement offers a clue. Entangled particles can affect each other instantaneously across vast distances, violating the spirit, if not the letter, of relativity. Einstein called it spooky action at a distance, but today we know it's real. Entanglement doesn't transmit information faster than light, but it does suggest that the universe is deeply non-local, that parts of the cosmos are connected not by space, but by something deeper: information, correlation, causality without distance. Physicist Mark van Ramstok proposed that space-time itself could be a geometric manifestation of entanglement, that the connectivity between quantum systems literally gives rise to the fabric of the universe. If this is true, then trying to find the edge of the universe is like trying to find the edge of a database. You're not looking for a wall, you're looking for a pattern. This is more than a mathematical curiosity. It means the universe might not be a thing, but a process in evolving computation, a relational structure of probabilities and measurements. Quantum mechanics, long confined to the world of atoms, may hold the blueprint for cosmic architecture. Gravity, in this view, is not a fundamental force, but an emergent phenomenon like temperature or pressure arising from the statistical behavior of underlying microstates. This is the logic behind entropic gravity, proposed by Eric Verlinde, who suggests that gravity results from changes in the amount of information associated with the positions of material bodies. In this model, there's no need for dark matter. What we perceive as gravitational anomalies could be signs that our assumption of gravity as a basic force is flawed. Changing our perspective reshapes the entire scientific conversation. Instead of asking, "What is space?" we ask, "What gives rise to the experience of space?" Instead of, "Where did the universe begin?" we ask, "How do beginnings emerge from timeless principles?" Instead of, "What is beyond the edge?" we ask, "What creates the illusion of edges in the first place?" These shifts are not small. They require us to rebuild the scaffolding of science itself, to acknowledge that observation is not a passive act, but a generative one. That reality is not a pre-existing stage, but a drama that unfolds through entanglement, decoherence, and measurement. Technology plays a crucial role in facilitating these shifts. Our instruments are no longer just eyes and ears, they are translators, converting abstract mathematical domains into data we can see. Quantum computers, for instance, may someday simulate space-time geometries or test theories of emergent reality. Space telescopes like James Webb are already seeing farther than ever before, not just in space, but back in time. They reveal galaxies that appear fully formed just a few 100 million years after the Big Bang, contradicting existing models and hinting at new forms of early cosmic evolution, perhaps linked to alternative theories of structure formation. LIGO and other gravitational wave detectors are opening a new domain of non-electromagnetic observation, offering signals from parts of the universe previously inaccessible. Each of these discoveries presses us to ask better questions, and better questions lead to paradigm shifts. Consider how our view of Earth changed once we saw it from orbit, not just intellectually, but emotionally, spiritually. The overview effect transforms astronauts not because they learned something new, but because they see it differently. Science works the same way. The heliocentric model of Copernicus didn't just replace a model, it changed the human role in the cosmos. Relativity didn't just revise Newton, it reshaped how we think about time. Quantum mechanics didn't just update classical physics, it shattered the idea of objective, observer-independent reality. These are not just discoveries, they are revolutions of perspective. Today, we may be on the brink of another. The edge of the universe, once thought to be a place we could reach with better tools, may turn out to be a misunderstanding, a misreading of a reality far stranger than we imagined. In a holographic or emergent space-time model, the edge is an illusion created by our embeddedness in a particular perspective. The real frontier is conceptual, not physical. It lies in our ability to reimagine space, time, matter, and even selfhood as dynamic, relational, and emergent. This perspective doesn't diminish the beauty of the cosmos, it amplifies it. It shows us that we are not merely observers trapped in space, but participants in a vast quantum story, co-creators of a universe whose deepest truths cannot be seen, only revealed through new ways of thinking. It invites us to see the cosmos not as a puzzle to solve, but as a mystery to engage with. And in doing so, it fulfills the highest calling of Sciencino to provide final answers, but to illuminate the pathways where wonder and understanding intersect. We are not at the end of the road, we are at a bend. And around that curve may lie not the edge of the universe, but the realization that edges were never the point. The shift in perspective tells us that what we've been chasing may not be a place at all. It may be a way of seeing one we are only beginning to discover. In every great story, there comes a moment when the audience is forced to reevaluate everything they thought they understood, when a single revelation turns the narrative on its head and exposes a reality far stranger, deeper, and more mysterious than anyone had expected. In the cosmic narrative of our universe, that moment may already be upon us. For centuries, humanity believed it could unveil the workings of the cosmos through persistent observation, the refinement of mathematics, and the application of rational thought. And indeed, we've made astonishing progress, from the heliocentric model to general relativity, from quantum mechanics to the discovery of dark energy. But just when we believed we were on the cusp of a unified theory, when the pieces of the cosmic puzzle seemed almost to fit, new discoveries and radical theories began to emerge that didn't just defy expectations. They shattered the very foundation upon which those expectations were built. Perhaps the most startling of these discoveries is the realization that our universe, as vast as it is, may not be the only one. The multiverse, once relegated to the fringes of speculative theory, is increasingly being treated as a serious contender in cosmology. This is not a single idea, but a family of theories, each suggesting that what we call the universe is merely one bubble in a sea of countless others. Some versions arise naturally from eternal inflation, the idea that the rapid expansion of space that occurred just after the Big Bang never completely stopped. In some regions, inflation ended and formed pocket universe seesaws among them, while in other regions it continued. endlessly birthing new universes with varying physical constants, laws of nature, even numbers of dimensions. In this framework, the conditions of our universe, so seemingly fine-tuned for life, are not evidence of design or necessity, but chance. We live in a universe that allows observers like us because we couldn't exist in any other. This idea overturns one of the most sacred assumptions in science, that our universe is typical, that its laws are universal, and that they can be generalized. If the multiverse is real, then the laws we've discovered might apply only to this bubble. Constants like the speed of light, the strength of gravity, the mass of the electronauts thought to be universal truths may be mere local rules, like regional dialects in a cosmic language. In another universe, gravity might be stronger, time might flow differently, or atoms might not even exist. And we would have no way to observe these other realms, as they lie beyond our cosmic horizon, causally disconnected from our own. But the implications are not just physical. They are philosophical and existential. The multiverse suggests that everything that can happen does happen somewhere. There may be other versions of you, living slightly different lives, in slightly different worlds. In one, you took a different path. In another, you never existed. If true, this idea could upend our understanding of identity, morality, and meaning. Are we truly unique? Does choice matter in a reality where every possibility is realized? These aren't just thought experiments. They are the emotional and conceptual shockwaves of a theory that breaks the boundary between what is actual and what is possible. And just when the multiverse seemed to be the boldest idea on the table, an even more disorienting theory began to take shape: the simulation hypothesis. Popularized by philosopher Nick Bostrom in the early 2000s, this theory asks a simple but unnerving question. If it becomes possible for advanced civilizations to simulate entire universes down to the level of conscious beings, and if such simulations become numerous, then what are the odds that we are the one civilization living in base reality rather than one of the simulations? Statistically, it is more likely that we are inside a simulation crafted, perhaps by post-human entities, advanced AIs, or beings from higher dimensions than that we are the original physical world. As absurd as this might sound, the simulation hypothesis is taken seriously by some physicists, computer scientists, and philosophers, not because we have evidence that we're simulated, but because we have no way to falsify the idea. And certain aspects of quantum mechanics, such as the observer effect, the pixel-like discreteness of space at the Planck scale, and the emergence of information as a foundational concept are surprisingly compatible with a simulated reality. The universe behaves like a computer in many respects. It stores information, it processes inputs, it evolves according to algorithms. Some even argue that the speed of light is a processing limit, that quantum randomness is the result of computation shortcuts, and that black holes are information sinks, not physical objects in the traditional sense. If either the multiverse or the simulation hypothesis is correct or even partially correct, then the implications are enormous. The universe is no longer a monolithic, self-contained reality, but part of a larger metasystem, governed by principles we may never fully access. Our search for the edge, the origin, the unifying equation may be like a video game character trying to understand the code that generates their world. And yet, rather than rendering our quest meaningless, these ideas force us to rethink the very nature of meaning. If reality is a simulation, who or what is the programmer? If we are part of a multiverse, is there a deeper law that governs the entire structure? Is there an ultimate reality beneath these layers of nested worlds? Amidst these wild possibilities, new observations continue to complicate the picture. The James Webb Space Telescope has revealed galaxies that seem to have formed earlier and more rapidly than expected, suggesting that the standard model of galaxy formation may be incomplete. Gravitational wave astronomy has uncovered black hole mergers that don't fit previous mass predictions, hinting at unknown populations of primordial black holes or new physics entirely. And increasingly precise measurements of the cosmic microwave background show subtle anomalies, temperature fluctuations, cold spots, asymmetries that could be signs of collisions with other universes, flaws in inflation theory, or shadows cast by higher dimensional structures. These findings all share one theme: They resist being folded neatly into our existing narrative. They are the plot twists of the cosmos' small details that, when seen from the right angle, reveal a hidden story. And as these anomalies accumulate, the scientific community faces a turning point. Do we tweak the models to preserve the current paradigm? Or do we embrace a new framework that may be stranger than we can currently imagine? The unexpected twist is not just in the data, it is in our minds. It is the realization that the universe may not be comprehensible in the way we once believed, that the rules may not be fixed, that the very notion of a final theory may be a mirage. And yet, there is a deeper twist beneath it, a quiet, humbling realization about our place in the cosmos. For so long, we believed that understanding would bring control, that knowledge would bring closure, that the pursuit of science was a march towards certainty. But the more we learn, the more we encounter a universe that is not only vast but self-transcending, a reality that seems to generate layers of complexity faster than we can reduce them. Instead of final answers, we find infinite recursion. Instead of a single truth, we find nested truths, each valid within its own domain, each pointing toward deeper questions. Perhaps the real twist is that the cosmos was never a puzzle to be solved, but a conversation to be had. We are not the center of this story. We are not even the sole narrators. We are one voice in a chorus, a temporary node in an eternal dialogue between order and chaos, pattern and noise, information and entropy. And that realization, rather than diminishing us, may be the most profound discovery of all, because it means that wonder never ends. That exploration is not a path to certainty, but a practice of cosmic participation. That we are not just observers of the universe, we are its way of questioning, reaching, and dreaming. In this new light, science becomes not a quest for domination over nature, but an act of reverence. The simulation, the multiverse, the holographic universe, these are not answers, but mirrors, reflecting our hunger to understand, to connect, to belong. The unexpected twist is not that the universe is more complex than we thought. It's that the very act of thinking, of asking, of imagining, is part of the fabric of reality. We are woven into the mystery, not standing outside it. And so we continue not because we expect to find the final edge, but because we've discovered that the search itself is the point. That every theory is a story, every measurement a line of poetry, every discovery a reminder that we are alive in a cosmos that is not only stranger than we suppose, but stranger than we can suppose. The twist is not the end of the story. It is the moment we realize the story has no end, that we are free to write the next chapter. Despite the staggering progress we've made in understanding the cosmos, from the early spark of the Big Bang to the accelerating expansion driven by dark energy, humanity now stands at a precipice. The closer we draw to the edges of knowledge, the more elusive they become, like a horizon that recedes with every step. And as we attempt to wrestle with the most profound mysteries in physics and cosmology, we face a host of new challenges, some technical, some conceptual, all daunting. These are not merely footnotes in the story of science. They are towering obstacles, demanding new tools, new methods, and a deeper rethinking of how we probe a universe that resists simplification. If the 20th century was the age of discovery, the 21st must become the age of innovation, not just in theory, but in the very way we search for truth. One of the most immediate challenges is the limit of our observational reach. The speed of light, the very thing that lets us see into the past and decode the early universe, is also a cosmic boundary. We can only observe the part of the universe from which light has had time to reach us, about 13.8 billion years worth of cosmic history, stretched into a sphere approximately 93 billion light-years across due to the ongoing expansion of space. But what lies beyond that horizon? More galaxies? Other universes? Fundamentally different physics? We can only guess. The observable universe is just a fraction of the whole, and it's entirely possible that we are missing the vast majority of what exists. Our best instruments, no matter how powerful, are trapped within a bubble of light speed limitation, and the horizon expands faster than we can chase it. Future discoveries, therefore, depend on how well we can infer the unseen from the seen. And even within that observable bubble, our tools are often inadequate for the precision we now need. The James Webb Space Telescope, JWST, the Atacama Large Millimeter Array, ALMA, and the Laser Interferometer Gravitational Wave Observatory, LIGO, represent the pinnacle of current observational technology, yet they're still not enough to answer many of the deepest questions. JWST has already begun to challenge assumptions about early galaxy formation, spotting mature galaxies much earlier in cosmic history than models predicted. But to follow up, we'll need more powerful telescopes, both space-based and ground-based, with broader wavelength sensitivity and higher resolution. We need the ability to detect fainter light, more distant signals, and weaker gravitational waves. The deeper we reach into the early universe, the more we need instruments capable of catching whispers in the cosmic static. This has led to a call for next-generation space missions, not incremental upgrades, but paradigm-shifting leaps. NASA's Nancy Grace Roman Space Telescope, set to launch in the coming years, will expand on JWST's legacy, offering a wide-field view of the sky and precise measurements of cosmic acceleration. Europe's Euclid telescope, launched in 2023, is already contributing to our understanding of dark energy and dark matter through large-scale structure mapping. But even these missions are only stepping stones. More ambitious proposals include LISA, Laser Interferometer Space Antenna, a space-based gravitational wave observatory that would detect lower frequency waves than LIGO can, opening a new window on massive black hole mergers and perhaps even ripples from the early universe itself. Projects like LUVOR, Large UV, Optical, IR Surveyor, and HABEX, Habitable Exoplanet Observatory, are being discussed as the next flagship telescopes designed not only to explore the deep universe, but to detect biosignatures on exoplanets and even image Earth-like worlds directly. But building these instruments comes with massive logistical and financial hurdles. They require decades of planning, international cooperation, and sustained funding across political administrations. They demand ultra-precise engineering and testing, and often push the limits of current materials science. Each mission represents a Gamblea multi-billion-dollar investment, with no guarantee of return, especially when success is measured not by utility, but by insight. And beyond the technical, there are data challenges. We are now collecting more information than we can meaningfully process. Massive sky surveys like the Vera C, Rubin Observatory's LSST, Legacy Survey of Space and Time, will generate petabytes of data each year, and making sense of it requires advancements in machine learning, pattern recognition, and artificial intelligence. Beyond technology, another major challenge lies in theoretical bottlenecks. The standard model of particle physics has been remarkably successful in predicting and confirming fundamental particles and interactions, yet it fails to incorporate gravity, the most pervasive force in the universe. Likewise, general relativity, while immensely accurate on large scales, cannot be reconciled with quantum mechanics. There is still no working theory of everything that unites these two frameworks, and without such a theory, we are left with partial descriptions of reality. Supersymmetry, string theory, loop quantum gravity each offers hope, but none has delivered definitive, testable predictions. The landscape problem in string theory, with its 10 qubit possible universes, and the lack of experimental evidence for supersymmetric particles, have made many physicists skeptical. We need new ideas, but we also need a way to test those ideas. Without falsifiability, even the most elegant theories risk becoming philosophical rather than scientific. Another profound challenge is the nature of dark matter and dark energy, two entities that comprise 95% of the universe, yet remain fundamentally mysterious. Despite decades of searching, we have not detected dark matter particles directly. Proposed candidates like WIMPs, weakly interacting massive particles, actions, or sterile neutrinos have thus far eluded discovery. Experiments like Xenont, Lux Zeppelin, and Pandax continue the search with increasing sensitivity, but each non-detection raises new questions. Are we looking in the wrong place? Is dark matter not a particle at all, but a modification of gravity? As for dark energy, we know almost nothing. Is it a cosmological constant? A scalar field? A sign of extra dimensions? Our models of cosmic acceleration can accommodate it mathematically, but they don't explain it physically. Understanding dark energy may require new physics beyond general relativity, perhaps from quantum gravity or an unknown fundamental force. Complicating all this is the Hubble tension, the growing discrepancy between different methods of measuring the universe's expansion rate. Observations of the early universe via the cosmic microwave background yield a lower value than those of the local universe via type Ia supernovae and Cepheid variables. The tension is now beyond the margin of error and may hint at new physics, such as early dark energy, changes in neutrino behavior, or flaws in our assumptions about cosmic structure. Resolving this conflict will require not only better measurements, but also re-examining the assumptions baked into our model. A humbling task for a field that prides itself on predictive power. In response to these challenges, scientists are reframing their approach. Rather than searching for final theories, many are now embracing a modular view of physics where different models apply in different domains, and the goal is to map the transitions between them. There is also growing interest in emergent theories, where space-time, gravity, and even quantum mechanics are not fundamental, but arise from deeper informational or thermodynamic principles. This opens new avenues of investigation, including the use of quantum information theory to study entanglement and entropy as the basis for space-time itself. Interdisciplinary collaboration is key. Astronomy is merging with data science. Cosmology is integrating philosophy. Physics is learning from computation and complexity theory. The next breakthroughs may not come from isolated geniuses, but from global teams, collaborative platforms, and hybrid thinkers who can bridge multiple fields. Projects like the Event Horizon Telescope, which imaged the shadow of a black hole by linking radio telescopes across the globe, demonstrate what's possible when knowledge is distributed and synchronized. The future of cosmology will depend on such collective intelligence, on building not just bigger telescopes, but better ways to think. Even public participation is evolving. Citizen science projects like Galaxy Zoo and SETI at Home enlist thousands of volunteers to classify galaxies or search for extraterrestrial signals. The democratization of data and the accessibility of tools mean that amateur astronomers can contribute to real discoveries. And in a world increasingly dominated by misinformation, scientific communication, the ability to tell the cosmic story clearly, compellingly, and responsibly becomes a critical challenge of its own. The emotional dimension cannot be ignored. As we push the boundaries of knowledge, we also push against the limits of human identity, existential meaning, and collective purpose. The more we learn about how small and temporary we are, the more urgent it becomes to understand why we continue the search. And perhaps that is the most universal challenge of all, to find value in the pursuit, even when the destination recedes. To recognize that science is not just about what we know, but how we choose to engage with the unknown. The next 100 years of cosmology will not be easy. The questions will grow deeper, the tools more complex, the theories more abstract. We will face dead ends, false hopes, and frustrating silences. But in each challenge lies an opportunity not just to know more, but to become more, to expand our imagination, our resilience, our ability to live in mystery without surrendering to it. The universe may never give up all its secrets. It may be infinite, holographic, emergent, or simulated. But as long as we are here to ask, to build, to wonder, the story continues. And that, ultimately, is what drives science forward. Not certainty, but curiosity. Not answers, but better questions. Not the promise of reaching the edge, but the adventure of always moving toward it. The challenges ahead are immense, but so is our capacity to face them, together, thoughtfully, boldly, eternally reaching for the stars. As we step into the final act of our cosmic journey, one shaped by curiosity, paradox, and discovery, the stage is set for a confrontation unlike any before. It is not a war of ideologies or politics, but of ideas so powerful they seek to redefine the nature of reality itself. For over a century, two great theories have ruled the universe. Einstein's general relativity, which governs the vast, graceful arcs of planets, stars, and galaxies, and quantum mechanics, which dances unpredictably in the microscopic realm of particles and probabilities. Each is complete in its domain. Each has been tested with unmatched precision, and yet they cannot coexist. This tension between the smooth continuum of spacetime and the discrete, jittery realm of quanta driven the deepest intellectual struggle in modern science. And now, with new tools, new observations, and new minds entering the arena, we find ourselves on the brink of a potential unification or a deeper fracturing of our cosmological understanding. Among the most ambitious attempts to resolve this divide is string theory, which proposes that all fundamental particles are not point-like dots, but vibrating one-dimensional strings. These strings oscillate at different frequencies, giving rise to the particles we observe, like quarks, electrons, and photons. The elegance of string theory lies in its ability to naturally incorporate gravity through one of its vibrational modes. But this mathematical beauty comes at a cost. It requires extra dimensions up to 10 or 11, in total most of which are curled up so tightly that they're undetectable at human scales. String theory also leads to the landscape problem, a near infinite number of possible vacuum states, each corresponding to a different set of physical laws. It can explain anything, and therein lies its greatest weakness. It predicts everything, and therefore nothing. Despite its theoretical allure, string theory has yet to make a single verifiable prediction, a fact that fuels criticism and caution within the scientific community. In response to this, a different contender has emerged: loop quantum gravity, LQG. This framework seeks to quantize space itself, proposing that spacetime is not continuous but composed of finite loops or chunks at the Planck scale. In this view, the fabric of reality is granular, and geometry becomes a function of quantum states. Unlike string theory, LQG does not require extra dimensions or exotic particles. It offers a more direct route to unifying quantum mechanics with general relativity. It has made progress in modeling the Big Bang as a big bounce, avoiding the singularity by proposing a prior contracting phase. However, LQG also struggles with testability and integration with the standard model of particle physics, which string theory handles more gracefully. Each theory thus holds part of the truth, yet neither delivers a complete picture. Meanwhile, a growing movement within theoretical physics is exploring emergent gravity, the idea that gravity is not a fundamental force, but a macroscopic consequence of deeper, microscopic processes. Inspired by thermodynamics and information theory, this approach draws analogies between spacetime and the behavior of fluids or elastic materials. One of the leading voices in this camp is Eric Verlinde, who suggests that gravity results from the entropic tendencies of information spread across space, not from mass attracting mass. In this paradigm, space and time themselves are emergent, arising from entanglement patterns in quantum fields. This view aligns closely with the holographic principle, which posits that the three-dimensional universe we observe is encoded on a two-dimensional surface at its boundary. Such ideas are revolutionary, but they too are difficult to test, as they often require observing phenomena at scales or energies far beyond current capabilities. At the heart of these debates is a deeper question. Does the universe have a boundary, a final edge, or a core set of laws that apply everywhere, eternally? Many physicists still believe in the dream of a theory of everything, a unified framework that would explain all forces, particles, and constants from first principles. But others are beginning to suspect that such unification may be impossible or even misguided. The universe may not be a single coherent system governed by eternal laws, but a patchwork of domains, each with its own emergent behaviors and approximations. Just as Newtonian mechanics works perfectly within certain limits but fails in others, so too may quantum mechanics and general relativity be only local descriptions of a deeper, shifting reality. This growing skepticism has led to a philosophical shift. Instead of assuming that reality is fundamentally comprehensible in human terms, some physicists are embracing a new humility. Perhaps we will never find a true boundary. Perhaps the universe is infinite in size, in complexity, and in law with no final equation, no ultimate edge, no master theory to wrap it all up. Instead of one grand unifying principle, we may be left with a hierarchy of models, each useful within its regime, but none absolute. In such a framework, the search for knowledge becomes less about destination and more about navigation, a continuous journey through levels of approximation and understanding, each revealing new vistas as our tools improve. This does not signal defeat. On the contrary, it points to the future of cosmology as an evolving, interdisciplinary enterprise zone that fuses mathematics, computation, philosophy, and even consciousness studies in pursuit of deeper coherence. The field is increasingly being shaped by technologies once unimaginable. Quantum computers that could simulate space-time at the Planck scale, AI systems that sift through petabytes of observational data to find hidden correlations, and gravitational wave observatories capable of detecting the faintest ripples in the structure of reality. The coming decades will also see the deployment of powerful new instruments: the Nancy Grace Roman Telescope, the Laser Interferometer Space Antenna, LISA, LUVOR, and HABEX. These missions are not just extensions of existing capabilities. They are instruments of transformation, designed to test theories on cosmic acceleration, dark energy, exoplanet atmospheres, and perhaps even biosignatures of alien life. In parallel, we are witnessing a new cosmological pluralism, a willingness to entertain multiple, even conflicting models, as long as they are productive. The multiverse is no longer dismissed as pure speculation. The simulation hypothesis is being refined with input from quantum information theory. Alternative cosmologies like conformal cyclic cosmology, causal set theory, and shape dynamics are gaining attention. Each offers a different view of time, causality, and existence. These competing visions may not converge anytime soon, but they form a rich dialogue, pushing the boundaries of how we think about the universe. So, where does this leave us? In a sense, the final confrontation is not between theories, but between certainty and complexity. We began with the hope of a unified cosmosa clockwork universe running on fixed laws, waiting to be decoded. But we now see that reality is more like an evolving conversation, shaped by what we can observe, what we can measure, and how we choose to interpret it. This doesn't diminish science, it elevates it. It makes the pursuit of truth an act of creativity as much as analysis, a dance between data and imagination, between what is and what could be. In the end, the future of cosmology may not lie in finding the final answer, but in building a framework capable of holding many truths, a network of theories that interlock like pieces of a multidimensional puzzle. Each theory will have its own edge, its own limitations, but together they will trace the contours of a deeper reality we are only beginning to glimpse. Perhaps one day we will find a bridge between the quantum and the cosmic, a logic that threads through all scales, weaving gravity, entropy, and information into a seamless whole. Or perhaps the search will go on forever, with each answer leading to a deeper mystery. Either way, the journey is not over. The edge of the universe, whether it's a boundary, a mirage, or a conceptual illusion, remains our ultimate horizon. And every step toward it, every theory tested, every paradox explored, is a testament to the enduring human spirit. We are, and have always been, explorers not because we expect to reach the end, but because we are drawn to what lies beyond the known. The final confrontation is not the end of the story. It is the moment we realize the story has only just begun. To explore the unknown is not merely an act of science, it is an act of the human spirit. At its core, it is a moral endeavor, a reflection of our deepest values and longings. We look up at the stars not only to understand what they are made of, but to understand who we are in relation to them. From the earliest cave paintings of constellations to the modern-day images captured by space telescopes, our fascination with the cosmos has always been a mirror revealing our curiosity, our vulnerability, our courage, and our refusal to settle for the limits of what is. The pursuit of cosmic knowledge is not just about the laws of physics or the architecture of the universe. It is about the architecture of the human heart. It is about what kind of species we choose to be when confronted with infinite mystery. Curiosity, that primal force behind every great discovery, is not a frivolous trait. It is essential. It is the engine of civilization. Curiosity drives us to leave behind the familiar and step into the darkness. It is the reason Galileo pointed his telescope toward the sky, despite religious dogma. It is the reason Einstein sat at his desk imagining beams of light and clocks on moving trains. It is the reason a team of scientists and engineers can spend decades building a telescope, knowing they may never live to see its data. To be curious is to be human. And to pursue curiosity in the context of the cosmos is to stretch the definition of humanity into something more universal, more enduring. It is to say, we are not content to simply survive. We want to understand. And yet, the cosmos does not yield its secrets easily. For every question we answer, 10 more arise. We learned that Earth orbits the Sun, only to wonder what lies beyond the solar system. We discovered galaxies, only to ask what came before the Big Bang. We measured cosmic expansion, only to be faced with the enigma of dark energy. In this way, science becomes a balancing act of tension between knowledge and mystery, between what we know and what we cannot yet even imagine. There is a kind of humility in this, a reminder that every insight we gain is provisional, every model subject to revision. The universe in its vastness teaches us the discipline of not knowing. It teaches us that we are not the center, not physically, not metaphysically, but that we are still meaningful. Because meaning does not come from dominance. It comes from connection, from participation, from being a conscious thread in a cosmic tapestry far beyond our comprehension. This is the deeper moral takeaway of cosmology, that the more we explore, the more we are called to be stewards of wonder. We are not just gathering facts. We are shaping a worldview, one that acknowledges both the brilliance of human intellect and the sanctity of mystery. This balance is crucial. Without mystery, science becomes dogma-rigid, closed, arrogant. Without knowledge, wonder becomes superstition-blind, ungrounded, lost. But together, they form a dance. Knowledge gives us power, while mystery gives us reverence. One fuels progress, the other cultivates awe. And in a world increasingly defined by short attention spans, political polarization, and technological overwhelm, the cosmos offers us a rare kind of clarity, a long view, a shared story, a common origin that transcends borders and belief systems. When we look at the Earth from space, we see no lines dividing nations. We see a fragile sphere of blue and green, suspended in darkness, protected by a wafer-thin atmosphere, vulnerable to its own inhabitants. The famous pale blue dot photograph taken by Voyager 1 as it left the solar system remains one of the most profound images in human history, not because of its technical achievement, but because of its moral resonance. Carl Sagan's reflection on that image reminds us that every war, every love story, every religion, every leader and peasant and child, all of it happened on that pixel. In that moment, astronomy became ethics. The act of looking outward became an invitation to look inward. It revealed the absurdity of our conflicts, the fragility of our existence, and the urgency of compassion. This is one of the great paradoxes of cosmic exploration. The farther out we look, the more clearly we see ourselves. The more we study exoplanets, the more we appreciate the miracle of Earth's balance. The more we model climate dynamics on Mars or Venus, the more we understand our own ecosystem's vulnerability. The more we search for alien life, the more precious our own biosphere becomes. And if we ever do find life beyond Earth, be it microbial or intelligent, it will raise not only scientific questions, but moral ones. How will we treat it? How will we share knowledge, resources, perhaps even culture? How will we define what it means to be alive, to be conscious, to be kin? Cosmology also humbles us with the scale of time. We are fleeting ephemeral beings born into a universe that existed long before us and will continue long after we are gone. The stars we see tonight may no longer exist. The light that reaches our eyes began its journey when early humans were just discovering fire. And yet, we are here brief. Bright sparks of awareness capable of mapping galaxies, decoding starlight, and wondering about eternity. In a universe governed by entropy and expansion, life is a kind of rebellion, a localized surge of complexity and intention in a sea of randomness. And human consciousness may be the most advanced expression of that rebellion yet known. With it comes responsibility not just to survive, but to thrive with purpose, to protect what is fragile, to seek what is true. The moral landscape of science is shaped not only by what we discover, but by how we choose to respond. Do we use knowledge to control or to connect? Do we exploit or do we nurture? Do we build walls of certainty or bridges of curiosity? The universe does not answer these questions for us. It poses them. It lays bare our smallness and our brilliance in the same breath. And it reminds us that wisdom is not the absence of doubt, but the ability to navigate it with grace. In the pursuit of cosmic truth, we also encounter the myth of finality, the hope that one day we'll find the ultimate theory, the last equation, the edge of understanding. But the more we learn, the more this myth dissolves. There may be no final answer. There may be no edge. Reality may be layered, recursive, infinite in its depth. And so we face a choice. Do we despair at this, or do we embrace it? Do we mourn the absence of certainty, or celebrate the abundance of possibility? The moral call of science is to choose the latter step into the unknown, not as conquerors, but as participants in a mystery that grows richer with every question asked. The cosmos also teaches us patience. The answers we seek may not come in our lifetimes. They may emerge slowly, across generations, through the collaboration of minds we will never meet. And so, science becomes a legacy projected gift we offer to the future. To build a telescope is to believe in tomorrow. To fund research is to trust in minds yet unborn. To ask a difficult question is to plant a seed of understanding that may not blossom for centuries. This is a radical form of Hopia belief, not only in knowledge, but in the continuity of wonder. In a world obsessed with immediacy, the cosmos reminds us that the most important truths take time. Perhaps the deepest lesson of cosmic exploration is that the unknown is not something to be feared, it is something to be honored. We are so often taught to seek control, to fear what we don't understand. But the universe shows us a different way. It invites us to live inside the question, to befriend uncertainty, to let mystery expand us rather than diminish us. And in that space between the known and the unknowable, something truly human emerges. A longing not just for knowledge, but for meaning. A desire not just to classify stars, but to feel awe. A call not just to look outward, but to grow inward. In the end, the stars are not our destination. They are our mirror. They reflect our restlessness, our creativity, our yearning to belong to something greater than ourselves. They show us that the universe is not indifferent, it is participatory. It does not give us answers. It gives us the capacity to ask better questions. And that, perhaps, is the true purpose of our species. Not to dominate the cosmos, but to be its witness. To stand beneath the night sky with wonder in our eyes and say, "We were here. We looked. We wondered. We tried to understand." And maybe that is enough. Maybe the meaning of life is not hidden in the final equations, but scattered like stardust through the questions we dare to ask. In that asking, that reverence, we become something more than intelligent apes on a rock. We become cosmic citizens, curious, humble, awake, and ready to keep going, no matter how dark the sky. Should the mystery of the cosmos ever be fully closed, should we one day reach a final theory, a complete map, an answer that silences all other questions? Or is the true power of science and the deeper meaning of cosmic exploration rooted in the openness of the unknown, in the continual reaching, not the arriving? These are not just philosophical musings. They are central to the future of how humanity understands itself in relation to the universe. For as much as we crave certainty and finality, there is something profoundly human and profoundly necessary about letting the questions stay open, about allowing the mystery to breathe. Throughout history, progress in cosmology has not come from closing off questions, but from opening them up. Every breakthrough has been a door, not a wall. When Copernicus displaced Earth from the center of the universe, it did not end the conversation, it deepened it. When Newton unveiled the laws of motion and gravity, it did not close the book, it revealed just how much we didn't yet know. Einstein's theories of relativity transformed our understanding of time and space, but they also exposed the limitations of Newtonian certainty. And now, with quantum mechanics, dark energy, and the possibility of multiverses or emergent spacetime, we are once again forced to reevaluate what we thought was fundamental. The history of cosmology is not a linear path toward final truth. It is a spiral staircase step offering a new vantage point, each level revealing broader horizons, each truth holding space for deeper questions. So what would it even mean to close the mystery? Would it be the discovery of a final equation, a theory of everything that perfectly unifies gravity, quantum mechanics, and all fundamental forces? Would it be a definitive map of the multiverse? A complete understanding of consciousness, space-time, and the nature of existence? The temptation of such a conclusion is undeniable. It would offer closure, confidence, and perhaps a comforting sense of order. But it would also risk something more fragile: our wonder. For if we ever believed we had reached the final word, what would drive us to look further? If we believed the story was complete, what space would be left for curiosity, for creativity, for the awe that has shaped our species for millennia? Leaving questions unanswered is not a failure of science, it is its fuel. Mystery is not an obstacle to be eliminated, but a terrain to be explored. And in space, that terrain is infinite. From the unobservable universe beyond our cosmic horizon to the quantum fields vibrating beneath our feet, from black hole information paradoxes to the structure of dark matter, the cosmos is an endless unfolding. Even the tools we use to examine either mathematics, our language, our perception are incomplete and evolving. We are not just navigating space, we are navigating the limits of knowledge itself. And there is no guarantee that those limits can ever be fully transcended. Yet this is precisely what makes cosmology so powerful, not because it provides closure, but because it invites participation. It is not a solved riddle, but a living story. And we are not passive readers, we are active characters, shaping the narrative with every question we dare to ask. Each new generation of scientists, dreamers, and thinkers enters the story at a different chapter, adds their own lines, and passes the book forward. Some answers are found, most are not. But in the process, we evolve not just in what we know, but in how we know. We learn to think more rigorously, to imagine more boldly, to live with uncertainty more gracefully. So let the mystery remain. Let it stretch out before us like the night sky, vast, brilliant, and impossible to fully chart. Because the value of that mystery is not just in what it hides, but in what it awakens. It reminds us that we are small, but not insignificant, finite, but part of something infinite, ephemeral, but capable of asking eternal questions. And perhaps the greatest lesson the universe offers is that not every mystery is meant to be solved. Some are meant to be lived. As we reflect on the biggest takeaways from our journey through cosmological thought, a few truths stand out, truths not about the universe itself, but about how we engage with it. First, our place in the universe is both humbling and empowering. We are not the center. We are not the reason for it all. And yet, we are made of the same elements that power the stars. We are expressions of the cosmos becoming aware of itself, capable of reflecting on its own origins. That is not a demotion. It is a miracle. Second, our knowledge is always provisional. Theories rise and fall, models evolve. What seems certain today may be revised tomorrow. This does not weaken science, it strengthens it. Because science is not a static collection of facts, but a dynamic process of inquiry. Its greatest strength is its ability to adapt, to self-correct, to remain open. Third, curiosity is the beating heart of exploration. It is what propels us into the dark, what keeps us staring at the stars, what drives us to build telescopes and particle colliders and spacecraft destined for the edge of the solar system. Curiosity is not childish. It is sacred. And when guided by discipline, collaboration, and imagination, it becomes the most powerful tool we have. Fourth, the cosmos teaches us to live with contradiction. Light behaves as both particle and wave. Time moves forward but is reversible in theory. Space can curve. Nothing can contain everything. The universe is not tidy. It is strange, irreducible, often paradoxical. But within that paradox lies possibility. The ability to hold conflicting truths without collapsing into confusion is not just a skill, it is a form of wisdom. And finally, the pursuit of cosmic understanding is a moral act. It reminds us of our shared origin, our shared future, our shared responsibility to protect the only home we know. It inspires global collaboration. It transcends borders and ideologies. It asks us to think in terms of generations, not headlines. To care not only for what is, but for what could be. to use our knowledge not as a weapon, but as a bridge. In light of all this, the question is not whether we will ever close the book on the universe. The question is whether we will continue to read it with reverence, with joy, and with an understanding that the last page may never come. And that's okay, because in a universe without boundaries, the search for answers becomes a way of life, a commitment to wonder, to humility, and to collective discovery. The infinite possibilities of space are not just out there, they are within us. Every new theory, every mission launched, every child who looks up and wonders, these are echoes of the same impulse. The impulse to reach, to imagine, to connect. We may never find the edge of the universe. We may never fully decode the laws of nature. But in trying, we become more than we were. We become storytellers of the stars, cartographers of the unseen, keepers of a flame that burns not with certainty, but with hope. So let the mystery remain open. Let the questions proliferate. Let the cosmos continue to unfold, not as a puzzle to be solved, but as a poem to be read aloud again and again across generations. Because in the end, it is not the final answer that defines us. It is the courage to keep asking, the willingness to remain open. The beauty of a species that, in the vast darkness of space, chose not fear but curiosity. And that, above all, is what makes us human.